Chapter 1, Classification of Matter. Chemistry, the study of matter. Matter, anything that has mass and occupies space. The air in this room occupies space. It's a gas. It doesn't have a whole lot of mass, but it does have mass, and it fills a certain volume. Anything that has mass and occupies space. The periodic table represents all the elements that are in the universe. So all matter is in one form or another, 1, 2, 3 or more of these elements. So the periodic table scopes out all of the matter in the world. We will talk about chemical properties and physical properties. The density of water is a physical property. Let me hand one other thing out. I know where I put it. On occasion, I'll have a worksheet. These aren't to be turned in. These are just, I don't know exactly how we'll use these, probably more along the lines of just something to spur a little bit of thought, maybe some questions you might have, so we can relate to this later. We can look at it and see if you have any questions as to what the correct answer is for some of these things. So these are worksheets. I don't know if I'll have one for every concept. So chemical and physical properties. Those are different. As I was saying, water has density is a physical property of water. I could take a little bit of water and I can go measure the density of it. It isn't in relationship to anything else, just water. How many grams per cubic centimeter is it versus gold or silver or anything else? It's density. That's a physical property. Chemical property is I could take sodium metal and drop it into water, and I get a reaction. I get an interaction that occurs, a chemical reaction that occurs between the sodium metal and the water. That's a chemical property of each one of those. Sodium reacts with water. Water reacts with sodium chemically to form a new substance. Not a new element, but a new compound. So chemical properties have to do with that material in relationship to the way it reacts with some other material. It's a chemical property. So we distinguish between those. Chemical changes and physical changes. You can take water and freeze it, turn it into ice. That's a physical change. You can take water and react it with sodium, and you're going to get a chemical change. All right, so there's a gold nugget. Yeah, Mark, is it? Can you turn this front light off? Some of these pictures pop a little bit better with the light dim. So there's a gold nugget. And there's a scanning, tunneling microscopic view of gold. So we can drill down into this a whole lot more. Electron microscopes, a little bit more common. Just a slide to just show you chemistry is related to many, many, many other fields. Environmental science, food science, agriculture, nuclear chemistry, chemical physics or physical chemistry, mathematics, engineering, medicine. There's a whole lot in medicine, chemistry, and biochemistry. So chemistry is related to many other fields. A whole lot going on here relative to medicine. understanding of cancer at a biochemical level, things like that. Yeah, so chemistry is related. SAWS, San Antonio Water System. They do an extensive analysis on our drinking water. They put on an annual report. You could go to saws.org and look for the quality, or I don't know which tab it's under, and then look for their annual quality report, and it tells you all kinds of things. Calcium, sodium, magnesium, lead, cadmium, chromium levels, THMs, whatever those are, trihalomethanes, all kinds of things that they monitor on there. And then microbiological results as well. So they've got a chemical lab. They've got a lab that's doing extensive analytical chemistry on our drinking water and reporting it. Ways to characterize matter. Elements by composition. Elements are compounds. By its physical state. It's a gas, liquid, or a solid. All right, so there's different ways of characterizing. Here's I guess an iceberg floating in the ocean with some clouds above it as an example. Right there in that photograph you see water, H2O, in 3 different forms: ice, liquid, and the gaseous form of water. So the ice, you have these H2O molecules, and the red is an oxygen, and the little white ones here are hydrogens, and generally you would see water represented in that kind of angle, like a boomerang. There's an angle. It's not a straight molecule. It's bent. And so there's the individual molecules right there with 2 hydrogens connected to an oxygen. Here are these individual molecules associating with other molecules into a crystal pattern. They're getting locked into a crystalline pattern, solid, and then there they are, closer than they are in the gaseous phase. They're closer, but they're floating around. See, I don't have a, you have got a bottle of water. Okay, so there's the liquid water. It has a definite volume, but it has an indefinite shape. It takes the shape of the container. Doesn't change the volume of that. A piece of ice doesn't do that. If I had a piece of ice in the bottom of this thing, I moved it around, the ice cube would be the ice cube. It's got a definite volume and shape. It's a solid. And gas or water vapor will expand to fill the volume of the container. So it doesn't have a definite volume. Gases can be compressed. They can be pushed down into, they can be pushed down, they can be so there's some air under pressure right there. I can pressurize it even more, eventually pop the balloon. But I won't. Okay, so gases, liquids, and solids. And you're starting to see now a formula to represent. Water is not an element. It's a compound made up of 2 elements. The periodic table is a table of all of the elements in the universe. So there's hydrogen, number 1, and oxygen over here, number 8. Those 2 elements make up water. So gases, liquids, and solids. Okay, Mark, if you could turn those lights on again for me for a second here. gases, liquids, and solids. So I'm going to get a liquid here. I got to move my stuff in case. You want to back up a little bit. You have goggles? No. I'll move this here. What are we going to do? Okay, there's a bottle. Here's a liquid. Gases, liquids, and solids. So there's about, I think I'm going to do 100 milliliters there. 50. Let's do another 50. We're not going to drink this. Put that away. Put that away. I don't want to ruin my computer, so I'll move it over here. All right. Liquid. Solid. Let's put the solid in there. Earlier, but I wanted you to see what's going in the balloon. You don't know what's going in the balloon yet. Maybe you do. But that's, so we got a liquid and a solid. So there's our solid, there's our liquid. There's our balloon. Probably should have brought something to clean this up with. Okay, so I'm going to try to blow up this balloon. There's our gas. Warm. We obviously got a gas. We got it pretty quickly. Actually, we'll just stand over there. Oh, I do, yeah. There we go. All right. We can come back to that in the semester and dissect what happened right there, what the materials are, what happened. But first, let me show you my laboratory. There's my laboratory. Now, Mark, if you can turn that light off, we'll see this a little better. I meant to bring the book, that book right there, 100 experiments you can do. So these are my grandkids, and Toph, and Judah, and Hadassah ran off by this point in time to get the picture. But yeah, but this is we can actually do a lot with this right here just by varying the amount of the powder that we put in there, and we can do a lot. We might come back to do it, but I mean, eventually you'll be able to write the chemical equation for that. What is the gas? How balance it? Do all kinds of things with it. But just to demonstrate the gases, liquids, and solids. And you can change that. So we started out with a liquid and a solid. There was air in there, but obviously another gas was being released when they contacted one another. Another gas was being formed, enough to pressurize the balloon. So there is a case now where we mixed a liquid and a solid, and we've generated a gas. We didn't have the gas in there, we didn't have the gas in there, but we produced the gas as a result of that interaction. Okay, Again, some view of things. So here's some cotton. There's a microscopic, a magnified view of a cotton strand, 40 time magnification. Here's an electron microscope view of the cotton. Here we're starting to look at it. We're starting to look at it a little bit more with the modeling of the actual. So these carbon, oxygen, hydrogen, making up that cotton strand. And here's a little bit closer view of it. So all we got here is carbon, oxygen, and hydrogen in this natural fiber. But the natural fiber is a linear fiber, but the fibers are associated and attracted to one another in a certain way to make this pattern, make this fiber. All right, so let's look at classifying matter a little bit. So we start out with everything that has mass or occupies space, all of matter. Does it have constant properties and composition? Yes. Then it's a pure substance. No. Then it's a mixture. Water is a pure substance. It has constant properties and composition. Water boils at 100 degrees C. Pure water. Doesn't matter when you're in New York or Moscow. It boils at 100 degrees centigrade. So it has some pretty predictable physical properties. It has a definite composition, H2O. So it's in the pure substance category. Mixtures. Mixtures are not going to have, the example I like to use is Kellogg's Raisin Bran. Okay? Raisin Bran is a mixture of bran flakes and raisins. And they'll have a little qualifier on the box. They'll say settling might have occurred during shipment. Otherwise interpreted as the raisins are in the bottom of this box. Okay? It shakes and all the raisins go down to the bottom. So your first bowl of Raisin Bran, you're like, man, there aren't any raisins in here. It's not a very good, it's not a normal constant composition. Yeah, there's a lot of different things like that. These tabletops, these desktops are a mixture. They actually call them a composite of wood fibers, glue, this, that, and the other thing. This isn't a compound. It might be pretty consistent in its composition because they've mixed things together. But if I started examining under a microscope, I'll say, oh, I think I'm looking at only glue over here, and I think I'm only looking at a wood fiber over here. It's pretty segregated in its composition. All right, so those are mixtures. So pure substances, can it be simplified chemically? If the answer is no, you're talking about an element. If your answer is yes, you're talking about a compound. So again, water's my best example here, and we'll have a slide here in a minute. I could take water and break it down into hydrogen and oxygen. I can simplify it further, but I can't chemically simplify it any further than that. Yes, there are subatomic particles in there, but those are not, that's not a chemical, to break it up, break up the nucleus of those things, that's a nuclear reaction, not a chemical reaction. So once I get to hydrogen and oxygen, I have broken it down into its elements, and the elements can't be chemically simplified any further. All right, so there's two kinds of pure substances. Sodium chloride in your salt shaker at home. If it says sea salt, it's got all kinds of stuff in there. sea salt. But if you got a box of Morton's table salt, it's predominantly sodium chloride. That's a compound. And it's made up of sodium and chlorine, and it can be broken down into that. So water, salt are some examples of compounds. Mixtures can be homogeneous or heterogeneous. So heterogeneous mixture would be like the Raisin Bran. Homogeneous mixture, I could take a teaspoon of salt and stir it around in water, and it will dissolve in the water, and it will be equally salty throughout that water. It's a homogeneous mixture. It's a solution, but it's a homogeneous mixture of water and salt. The air in this room. So mixtures don't just have to be liquids or solids. They can be gases. Air is a mixture. So let's put in air here. Air. It's a homogeneous mixture of nitrogen, about 80%, and oxygen, about 20%. There's a little bit of carbon dioxide and some other things in air, but those are the major components of air, and it is uniform. If I took a sample of air in that corner of the room and another sample of air in that corner of the room, it's basically going to come up with the same composition. A Valero gas truck pulls into a Valero gas station. It's going to pump this gas down into one of their tanks. It is a mixture of a whole bunch of different organic compounds. Pentane, hexane, octane, isomers of those. We could do an analysis on it and say, well, there's 40 different organic molecules in there. So a little ethanol, but those are soluble in one another and uniform. It's going to have a uniform or homogeneous composition. All right, so we're already starting to see a little bit at the molecular, at the atomic or molecular level. Hydrogen, we're depicting that as H2. I'll write these a little bit bigger here. Oxygen, O2. Phosphorus, pure elemental phosphorus. 4 phosphorus atoms will associate with one another into this little quad. Sulfur, I want an S there first. Sulfur, it will be 8 sulfur atoms that associate with each other into a ring, but those are elements. So these are all elements. And then these are compounds. Compounds are made up of 2 or more elements in a fixed ratio. So we have H2O, CO2, and then C6H12O6, or glucose. You will start getting used to seeing these in the models. Carbon, oxygen, hydrogen. So, and it's arranged in a certain way. That's what the glucose molecule looks like. Could anyone make other molecules out of 6 carbons, 12 hydrogens, and an oxygen? 6 oxygens, yes. There's other compounds that you could make out of them, but that's the way glucose is arranged. That's the way carbon dioxide is arranged, carbon with 2 oxygens. And it's linear. Carbon dioxide is linear. Water is bent. Fancy that. All these questions are questions that people thought, why is that? They've tried to figure it out. And they have figured it out. And we'll get a little exposure to that. Why is water bent? Does it matter? You probably would be just as fine if it were linear. All right? But it's bent, and it actually has an impact on its properties, that it is bent. Okay, we talked about compounds and elements. Compound can it be broken down into anything simpler? Here's an example of water where they're using electrolysis or electric current to break the water down. So on one side, the negative post of this setup, we have hydrogen being formed, and on the positive side we have oxygen gas. Hydrogen is a gas, oxygen is a gas at room temperature. Elemental oxygen, elemental hydrogen. So here is where that compound, water, is being broken down by electrolysis into its individual elements. So let me just point out here, you can see this periodic table, you can see a bunch of things in red. Those are gases at room temperature in their elemental form. Hydrogen, oxygen, I mentioned nitrogen that's in air, fluorine, chlorine. The noble gases are gases at room temperature. The black ones, which are the predominant ones, and the black ones are solids at room temperature. And the blue ones, bromine and mercury, are liquids at room temperature. There's two that are liquids, most of them are solids, and then a few that are gases. I had a student from China one semester, and it just so happened to be that semester, in the same class, China, Russia, Philippines. I had students from all over the world in this one class, and so I said, well, I tell you what, why don't you go out there and look up the periodic table in your language, or how do you relate to the periodic table in your country? And one of the points we're making is that they're all arranged this way, whether you go to Russia. Matter of fact, it was a Russian chemist that got us on that path to arrange the elements in the periodic table that way. That's going to be module 3, I think it is, periodic table. But the interesting thing, the student from China brought in her Chinese one, and of course you're familiar with the Chinese symbols. There's a lot of information packed into a Chinese symbol in their language. And she said, oh, we can look at the symbol for hydrogen, oxygen, anything, and actually embedded in our symbol for that element is whether it is a gas, liquid, or a solid, room temperature. So they didn't have to color code it. They had a little thing that came off the side if it was a gas, something else if it was a solid. So right embedded in their symbol was what physical state it's in. Okay, so that's just an example of breaking down a compound back into its individual elements. Here's another example. See, I don't do every demonstration right in class. Here's one. What would be coming off of here would be mercury vapor. Okay, so you'd have to do this in a hood. This is mercuric oxide. And if you took that, it's a powder, and if you took it and heated it up real hot, it would decompose into mercury and oxygen. So the oxygen would flow out of the test tube, and you'd be left with a little puddle of mercury. When it cooled down, you'd have a little puddle of mercury in here. But mercury is poisonous, and it is a liquid at room temperature, and it has a little bit of a vapor pressure. So if you had a beaker of mercury here, you wouldn't get a lot of mercury off of it, parts per million mercury. But if you were in that atmosphere long term, you would be inhaling a little bit of mercury, and it would start accumulating in your body and cause some problems. So it's a heavy metal, and mercury, lead, chromium, there's a bunch of heavy metals in there that are toxic. Okay, we're back to this slide. I'm not exactly sure why. Got the same thing here. I don't think there's any further point. So I think we're all right there. Just some more examples. Italian salad dressing, oil and vinegar. Anybody want to guess what I did here?
Baking soda.
Yeah, basically. It's vinegar and sodium carbonate. So I didn't use baking soda, but I used sodium carbonate. Baking soda would be probably sodium carbonate and sodium bicarbonate, mixture of the two to some extent. So, but yeah, basically. So I just brought that up because vinegar, oil and vinegar don't mix. You can see two things right here. The oil is not soluble in the vinegar, and the oil is lower density than the vinegar. The oil's on top. It's floating on top of the vinegar. And so you always shake up your Italian salad dressing and then put it on your salad. Otherwise, you're going to get mostly oil or mostly vinegar. Because it is a heterogeneous mixture. Even when you shake it up, it's not forming a solution. You're just dispersing oil bubbles kind of non-uniformly through the salad dressing. But a G2 power drink or electrolyte drink is homogeneous. Everything that's in there is soluble in water, and it forms a homogeneous solution. Physical properties and change cause recognizable change without changing chemical composition. Chemical properties and change, they cause a change in the substance. They create something new. So the candle burning is consuming the composition of that candle. It's carbon and hydrogen, but it's burning, and it's producing carbon dioxide and water. So you're starting out with candle, but now a chemical reaction is occurring. The candle plus oxygen is forming carbon dioxide and water. But when you boil something on the stove, you're converting the liquid water into steam, but it's still H2O. You haven't produced anything of any new composition. All right, so iron rusting is a chemical property. That's a chemical property of iron. Rust is iron oxide. It's a new material. It behaves differently than iron. It flakes off, and your chunk of iron starts disappearing as the rust falls off of it. That's a new material. Chromium. So you can take iron and chrome plate it, and it looks like silver, and it doesn't rust. Doesn't rust. A galvanized bucket is iron with a zinc coating on it. Doesn't look as pretty as chrome plated stuff, but it doesn't rust. That's galvanized. What's the other example I was going to... Aluminum. Aluminum is an element that, like iron, it's a metal. So here's aluminum, here's iron. They're both metals. This rusts and flakes off and disappears. You know, a car that's 10 or 12 years old, not so much in Texas, but maybe down at Corpus Christi or up in Detroit, it starts rusting. You know, metal parts on the car are rusting and deteriorating. Aluminum doesn't do that. It does form a really microscopic coating of aluminum oxide, but it doesn't oxidize any further. So if you took aluminum and polished this up a little bit, it would look a little shinier because you're getting that little tiny film off of it, but it does not flake off and therefore disappear over time. It doesn't rust like iron does. But rusting is a chemical change. And just some other examples. I guess these are all chemical. You put copper in nitric acid, and you get off a gas, a brown gas. The solution turns blue. It's a chemical change. You take a match and burn it. It's chemical change. You're not putting a match back in the matchbox. It decomposes. Bananas ripening is a chemical change going on. Bacterially driven, but a chemical change. And cooking meat will cause the iron in the meat, any blood left in the meat is getting oxidized and changing colors as you're grilling the meat. Let's see, I think there was. It's mentioning the periodic table. To what extent here? Yeah, so this is mentioning the colors, and it's telling you whether it's a solid, liquid, or gas. Metals, non-metals, metalloids. We'll talk about that when we get to periodic table a little bit more. And maybe today I think I have these periodic tables to give you. So some definitions. We've already mentioned this: matter, anything that has mass and occupies space. Composition, the types and amounts of simpler substances that make up a sample of matter. Properties can be broken into physical and chemical. Physical, those which the substance shows by itself without interacting with anything else. Color, melting point, boiling point, density, some examples of physical properties. Chemical properties, that which the substance shows as it interacts with or transforms into other substances, such as its flammability. Things that burn are reacting with oxygen. Corrosiveness. And then you could talk about other things, but you're always going to be talking about how this reacts with that. You're talking about specifics in terms of chemical properties. Yeah, so an icicle melting is a physical change. Breaking water down into hydrogen and oxygen is a chemical change. Okay, let's just do this together. What do you think? Physical or chemical? The hardness of a material. Physical. Flammability. Color. Physical. Color. What color it is really how it's interacting with light. It's not undergoing any chemical change. So copper's color or hue would be the physical property of color. Compressibility. Physical. If I take gas and just exert a pressure on it, I can change the volume in which that gas is. We'll compress it, but it's still the gas. It's just closer together. Reactivity. Chemical. And then you'd have to specify, like, with what? We talk about these metals, so this family right here being the most active metals, the most reactive. So what we're basically saying, they will react with a lot of things. You know, potassium will react with lots of things over here. Silicon and phosphorus and sulfur and fluorine and iodine is a highly reactive metal. Sodium. Francium is so reactive, you can't get it all by itself. You can't order a bottle of francium and get it sent here. It reacts with the bottle. It's that reactive. So reactivity, it can be a relative thing. Potassium is a metal, iron is a metal. But iron isn't quite as reactive as potassium. That's why we don't make our cars out of potassium. They would react in the first puddle they went through. But iron it will react with water, it will corrode, but slowly. Magnetism. Physical. It's a physical property. So iron is ferromagnetic, and you just need a magnet to test it. It doesn't change the properties of the iron. All right, let's do a couple more changes here. Wood decaying. Chemical. If you took wood chips and you put them into a compost pile, it's not just, you're not just going to get smaller wood chips. It's going to turn it back into dirt, compost. Bacteria are actually eating the cellulose and breaking it down into other things. So this is a chemical change. Water freezing. Physical. Dry ice evaporating.
Chemical.
Physical. What is dry ice? You know what dry ice is? It's very, very cold. You can go to H-E-B and buy a chunk of dry ice. Not most of them. Not all of them can't carry it. Dry ice. Regular ice leaves a puddle. Dry ice, you do a play over here and you want smoke, you go get some dry ice and blow air on it and you get this little cloud. It's carbon dioxide. And it would be a solid, and what you have is carbon dioxide going to become a gas without going through the liquid phase. Doesn't go through the liquid phase. It goes right from solid to gas. That's unusual. Water goes from solid to liquid to gas. But that's a physical change. I'm writing it like it's a chemical reaction, but you can see we've got CO2 on both sides of that. It hasn't changed its composition. It's just changed its physical state. Digesting, so this is a physical change. Food digestion. Chemical. You are breaking it down. You eat a piece of meat, it's protein, your body digests it into amino acids. It chemically breaks bonds and breaks it down into these amino acids. I think that's the last slide. Take a look at your worksheet and just see if they've got any questions on any of those. You don't have to turn this in. This is, everybody get one? Is that pretty self-explanatory? Okay, and then let's take a peek at the syllabus. I think I just had one day for this topic. And so what we need to do let's see. Yeah, so on Tuesday, we're going to get into the atom. I will get back to my office, and in the next hour, there's a couple things I'll do. I'll open up the slides for Module 2. I'll take a look again at the dates on the Module 1 assignments. I'll probably open up the Module 2 assignments. I'll open those up. Probably not the quizzes yet, but the assignments. So you have Module 1 assignments, and there's 6 of them. Module 1 quizzes, there's 2 of them. And then you'll have the Module 2 assignments that you can start working on. I don't want to be the one holding things back. I don't want you to get too far ahead. I don't want you to get too far ahead, but I want you to be on track when we get to the atom on Tuesday, that you take a look at it. I assume you can go into the assignment and come out of it and go back into it again later. Is that right?
Yes.
Without submitting it?
Yeah.
Okay. So feel, and you can, let's finish this off. I'll get you your period.